In your project, you're going to have 10 classes. You're going to get 10 numbers. Probability that A is more likely, probability that C is more likely, probability that E is more likely, all the way to Z is more likely. You're going to calculate in your code 10 numbers. And then what? Take the highest, whichever is more likely. And that'll determine which class you call your unknown. You're going to have an equation for F for your distribution. We're going to take the log before we do that. Yep. And I'm going to emphasize that again later. Right now, I'm trying to make sure you get the general ideas down. This distribution is going to be different for every class. It could have a different covariance matrix, and it will definitely have different means. The means of each of your 8 features are different for A's than they are for C's than they are for E's. Okay. And your A priori probabilities, those are going to be the same. Is this stuff starting to look a little bit less confusing than it did 2 days ago, a week ago? You're not the only ones who get confused by it. That's why I'm happy to go over it again, because I know that all these equations here just, students panic. What do I do with it? You're going to be calculating equations. Grad students will be calculating equations for the homework 3. You do not calculate this sort of equations for the project. You can do it all numerical based on the distribution function for the Gaussian, though. So we're not going to go through all of this. We're going to start basically with this. Okay, what if the covariance matrices are not equal? We're still going to have this general form. Take the log of both sides. Oops, I left the a priori probabilities off. Add the a priori probabilities into there. We're still going to take the logs to form what we call discriminants. Put those a priori probabilities in there. Those a priori probabilities show up in your k's, just a constant. That's what I get when I type things up. Okay. And in your project, you're going to calculate discriminants by taking those logs. So you're not going to code an exponential. You're going to code this form, which is the log of your distribution function. And scaled by your a priori probability. How many probabilities are there going to be? 10 classes, 10 a priori probabilities. But your X and your mu are going to be 8 element vectors, and your sigma is going to be an 8 by 8 matrix because you have 8 features. Take the logs of both sides. The stuff that's out front And these a priori probabilities turn into constants. And the exponential goes away, just leaving you a quadratic.
When are we going to start project?
I'll post it this weekend and probably give you a week and a half to 2 weeks. I didn't want to distract you from the homework before, but I do want to keep talking about the project as we're going through this, to maybe get rid of some clouds of confusion before we get there. Keep relating this to the project. It should be kind of obvious that if we're doing Bayes, you're going to do a project with Bayes. You know what your data set is already. You kind of know the configuration of things. You've got enough work to do to get that homework done. Particularly those of you who have not started it. Okay, so you're going to take the log of both sides to get discriminants. We're going to then compare how many different discriminants in the project? 10. One for each class. And we take whichever one is largest because it's, with log being a monotonic function, it's going to be the same probability of which class is greater given your measurements. If we take the original or if we take the log. And the log means we don't have round off errors, or not as significant of them. So with numbers, because our variances are equal and the covariances are 0, our contours are going to be circles. But because they're not equal to each other, now this is an ellipse. Because sigma 1 is not equal to sigma 2, our decision boundary is no longer linear. Only if sigma 1 equals sigma 2 do we have linear decision boundaries. If sigma 1 is not equal to sigma 2, we do not have linear decision boundaries. We're now moving up into quadratics. Remington? You can see the difference between the blue and the red, maybe. The decision boundaries where the blue and the red hit. Preston, can you sort of see the boundary?
Yeah.
It's not red and green. Let me know if you can't and you can change the colors. Okay. Now here, they're not equal to each other, so we know we're going to have a quadratic decision boundary, but also what shape are our individual contours going to be? Pardon? Ellipses. No longer circles. Circles when the standard deviations are equal to each other. Ellipses when they're not. And it's going to be an up and down, left and right ellipse. It's not going to be tilted. But they're going to have different size ellipses. And the boundary will be an ellipse. So we're always going to come up with something quadratic if our covariance matrices are not equal to each other. Always something quadratic. And all conic sections are possibilities, including the degenerate ones. We'll get there. So you can have a general form for any conic section. Conic sections are taking pairs of cones, putting them tip to tip, and taking a plane and intersecting it. So if that plane is parallel to the edge of the cone, you get a parabola. If it is horizontal, you get a circle. If it is almost horizontal, but a little bit tipped, but not enough to hit the other cone, That's your ellipse. And if it's vertical or almost vertical, it's a hyperbola. And remember, these can rotate all the way around. They can have different orientations. All those different things are conic sections. They're all going to have some possibility here. Now, depending on what these values are relative to each other determines what you have. If A is 0, B is 0, and C is 0, what do you have? A line. How is that a conic section? Where would that plane have to be? That plane would have to be right there hitting that boundary. Okay. That's a degenerate case, degenerate conic section. That's if A, B, and C are all 0. You get a plane, whoops. Pretend my drawing is better. It's not easy with a mouse. That is parallel to the edge there. Now, another possibility is when A and C are equal to each other and B is 0. And A and C are equal, which shape is that? That's a circle. You'll have ax squared, cx squared, but A and C are equal. That's a circle. What if A and C are not equal? It's an ellipse if they're both positive and not equal. And if they have opposite signs, then that's your hyperbola. Sound vaguely like something you might have heard at some point in the math course? They don't teach this too much anymore. I really appreciate the pre-calc class I had in high school as to the nice things that they pushed us into doing there. And I see it's missing a lot from the curriculum. So I'm hoping that you've had some aspect of that. Now, another possibility, another degenerate one, is if we take a plane that's perfectly upright, pretend that's an upright plane, cutting right through the middle of your cone. What shape is that? Sort of. She said absolute value, sort of. It does kind of work out to that. Because you're going to have that x squared equals y squared. So the A and C will have opposite signs. And they'll be equal. Get rid of some of the other stuff. If x squared is equal to y squared, how do we solve that equation? It has to do with that absolute value. You were not wrong, you just weren't all the way there. When you take the square root of something, you got to take the plus and minus square root. Vaguely, cobwebs pushing aside here, sound like something you heard once upon a time, but you haven't used in 20 years. Oh, no, not 20 years. Haven't used in 10 years, 7 years. Sound familiar? However long ago was, some of you are not even 20 years old, so it can't be 20 years ago. Okay. Some of you are just barely 20. Right? Some of you are just barely 20 over in that corner. Okay. So you take the square root of both sides. Because of the square root, you need to have a plus and a minus. So x can be plus and y, negative y, or y can be plus and minus x, depending how you want to look at it. And that's 2 lines. If I put a 4 there, x squared is 4y squared. Now they have different slopes that are not equal to 1. That is a hyperbola, a degenerate hyperbola. So you're going to have the a and the c of opposite signs. Get rid of a lot of this other stuff. And that's when you get 2 lines that are intersecting each other. Okay, I'm not just going through this because it's fun stuff. I love that part of the math course. That was one of my favorite math courses. I've had a lot of favorite math courses. I like math courses. Okay, but I'm not just going over this because it's a fun thing in a math class. Why am I going over this? Think back to the homework for those of you who've looked. The second problem in the homework, I give you a bunch of parameters for how to set up your means of your x's and your means of class 1 and your means for your class 2 and your standard deviations for class 1 and your standard deviations for class 2. And you're going to create these things. Now I give you 9 cases. And I've picked them carefully. They're not just randomly picked to give you some of these special cases. So you'll see some of these cases. Graduate students get to make nice equations. Undergraduates get to look at pretty pictures. But I don't want undergraduates just to look at pretty pictures. I want you to think about those pretty pictures. Yeah, it's that thinking stuff. I want you to think about those pretty pictures and say, what shape is it? Even if you don't have the equation, you can see the shape. So what shape do we have here? Ellipse. What shape do we have on the previous slides? We had some circles. We also had straight lines. And I bet one of the cases is going to be a parabola. And you'll have a hyperbola someplace in there too. And I then want you to go find whichever shapes are missing. So try different values of the means and the covariances until you can find something that gets you each of these different cases. And see, you can check mark that you've got not just these 4 cases, but also the degenerate ones of a single line and 2 intersecting lines. Play with it. You don't need equations for those extra ones. Grad students need 9 equations. But after you get those 9 equations, play with it. At that point, it starts to become easy. It should be sort of fun-ish, maybe a little bit, where you're just typing numbers into the GUI, saying plot, and looking at it, and get a feeling for what your choices are. What happens when your covariance is 0? What happens when it's not 0? What happens when the means are close? What happens when the means are far? What happens when your covariance, when your variances and covariances are equal? What happens when they're not equal? After you get through the drudgery of doing the stuff I told you have to do as a 9, play with it. You have to do 4 more and just report the results. But go ahead and play with it more than just those 4. Don't just pick 4 that are almost the same as each other. Pick 4 really different ones. Because after you get through those 9 cases, at that point, it should turn into sort of fun because you're just clicking away at the GUI and just saying, well, what do we get? What do we get? And at that point, it should be easier and more enjoyable. So lots of different shapes are possible for our decision boundaries, because we're always going to have something with these quadratics. There's some standard forms that things tend to show in. And these are the 9 cases that you need to do. For distribution 1, red, distribution 2, blue. Okay. And this is all of what we're doing with Bayes. Give it an unknown point. Choose class 1 if based on the measurements, class 1 is more likely. Choose classification 2, class 2, based on the measurements, class 2 is more likely. So we're looking to say which one is greater than the other. And for each class, based on your training set, you're going to calculate a covariance matrix, and you're going to calculate a mean for each class based on your training set. That's probably the hardest part of the project. Okay. It's not hard, but if you can't get there, you're kind of stuck. Then for each unknown point, you're going to measure the feature. That's your row in your eval 1, eval 2. And you're going to calculate your discriminant function with that x value corresponding to the feature in your eval set. Do some writing, please. You're going to want to have some notes on this. Even if I post these, you're going to want to have some of your own notes. And when you take that log, you wind up with this equation at the bottom. How many discriminants are you going to calculate for every point in eval? 10. And do what with them? Determine the highest, or which class goes with the highest. So that discussion I heard at the beginning about trying to figure out which is biggest, which is smallest, you're going to have to do something similar to that. But instead of doing which is biggest, which is smallest of distances to 100 points, which is biggest, which is smallest of 10 different discriminants. And here, it's not a 3 Bayes, it's always a 1 Bayes. You always want the one highest. So always looking for the one highest probability. Make sure you're taking notes so you're clarifying your brain, you know what you're going to do. Because everything always sounds really clear when I say it. But it's not nearly as clear when you guys go home and have to say it yourself.
The training data, set data is still going to be the same as last time.
Using the same data set, which means in your report, you can use a lot of the same wording. I do not take off points for self-plagiarism. I do take off points for partner or neighbor, colleague, internet plagiarism. But you can definitely reuse parts of your own reports. You can reuse parts of your own code. What parts of your code might you reuse? Reading in some data. Confusion matrix, outputting confusion matrices. What else? Normalizing your data. Sorting, some of your sorting code you might be able to slightly modify. And again, it depends on how nicely you structured your code as to how much you can reuse. Because you have some terms that are going to be the same across all 10 cases, you may drop them off in your code so long as you leave a comment to yourself about the fact that these were left off because of, if you reuse your code later for some other project, the 2 pi's will always be the same. Actually, there's a d over 2 missing out here. The d over 2 pi's will always be the same. But your log of p, your a priori probabilities will not always be the same in all future projects. So you might want to still leave that code in there, or at least enough commenting that if you ever do go back to your code and the project changes, that you've got something in there that you can, don't accidentally, oops, leave something out. It's really critical. You're going to want to find some code to do calculating discriminants of matrices. I bet it's out there, whatever language you've chosen. You're going to want to find some code for taking inverses of matrices. I bet it's out there, no matter what language you've chosen. You'll want to find some code for doing matrix multiplies. I bet it's out there, no matter what language you've chosen. What are the dimensions? Sigma is 8 by 8. X is 8. We usually talk rows first, so 8 by 1. This is critical. Mu is 8 by 1. Sigma inverse is 8 by 8. When we take these 8 by 1s and transpose them, they're 1 by 8s. And then another 8 by 1. What's this one? Scalar. What's the dimension of the determinant of sigma? Scalar. What's the dimension once we've multiplied your x transpose sigma inverse x? Scalar. If you get your dimensions right. Check your output. If you're not coming out of scalar, rewind, try something else. It's not that bad once you put the pieces together. Remember, it all comes down to it all comes down to choosing the class which, given your feature measurements, has the highest probability. That's where everything Bayes boils down to. And this is really, I say it, why am I saying it over and over again? Just because I have nothing else to say and I'm trying to fill up space? Not just common mistake, but really a critical concept for Bayes. The hope is that all of you are going to finish this course and go off somewhere. And maybe you'll talk to somebody about this material sometime in the future. And this is what you really need to call up is, well, what's Bayes? That's Bayes. Choosing the class that based on the measurements is most likely. The rest is just math to make it happen. But this is a really, really important concept that's associated with Bayes. Yes.
My brain's just not working right now, but it's still back to you.
Question on the previous.
This is fine. The first bullet point, each class based on sigma I and I. What are the
That's on the next slide.
okay, perfect.
And I told you those, that's going to be the hardest part of the project is calculating your sigma I mu I. And it's not that hard. Okay. But the training procedure is to take your training set and calculate your covariance matrix and your mean vector for each class. How many covariance matrices are you going to calculate? 10. How many mean vectors are you going to calculate? 10. Then for each testing, for each unknown point, you have a measurement of X, but you're probably reading it as a row vector, need to turn into a column vector. Common mistake. Calculate your discriminant. Add the d over 2 by the 2 pi. And then if you have more than 2 classes, you choose the class that provides the maximum probability. Out of your 10 classes, which one has the greatest probability? You can and should use the discriminant instead of the original probabilities to avoid round off error problems. And yes, the log of 2 pi is optional. Choose the class as the largest discriminant, which is equivalent to the class with the largest probability. If you have more features, you got more elements in sigma to calculate. See, it's bigger. And you're comparing the logs because the exponent gets very small very quick. I'm hoping I've said this enough times that all of you do this. Past semester, there's always somebody who didn't quite get the message. You're going to do 4 different things. First one is a minimum distance moment classifier, which is easy. You don't need to actually calculate sigma. You're going to set sigma to I to the identity matrix for each class. So your question of how do we calculate it, you don't need for part 1. Just set it to I. And that's going to turn into a distance to each of the means. The minimum distance classifier. And you can calculate the discriminant, or you can get rid of some of the scale factors on the negative side and change it from a discriminant to a score. But if you get rid of the minus sign, instead of looking for max probability, you're looking for minimum score. That score here is a distance.
So the covariance matrix is I because they're independent.
Because I'm telling you to program a minimum distance classifier, and a minimum distance classifier has a covariance matrix of I. So the first part of the project, set sigma to I, period. Calculate 8 mu's. Nope, 10 mu's. Calculate 10 mu's, set sigma to I, and go forth and classify. That's part 1. sort of, maybe. The second part, we're going to make identical covariance matrices. So we're going to assume that all of them are equal, but the means are not equal. That's going to make a linear classifier, as we talked about already. If the covariance matrices are equal, it's a linear classifier. Those squared terms are going to go away. Even when we get to more than two classes, you're not going to look at the decision boundaries. You're just going to know that they're linear. Because you've seen these other examples I did earlier, which showed you the squared terms drop away. And so you understand why they drop away, even if you go to higher dimensions. Instead of just x squared, y squared, it's x1 squared, x2 squared, x3 squared, x squared 4, x4 squared, all the way down to x10 squared. All those squared terms go away. And all the cross xy's go away. Because they're, it's going to be a linear classifier. And you're going to take your individual covariance matrices and you just add them up and divide by 10. We'll get to calculating the covariance matrix in a minute. The question was that. And that's we're going to have, therefore, the average of your covariance matrices is going to be what you're going to use. The third part of the project, we now are going to use the individual covariance matrices, 10 different covariance matrices, 10 different means to do the classification. And the fourth part of the project is going to be the same classifiers there, but you're only going to use the first 4 feature values. M00, mu20, mu11, mu02. We're going to skip the third orders. I'll have the whole in print. And I don't show it. Okay. Then how to calculate sigma. I've got this on a slide earlier in the slide deck. It's someplace earlier. Where we've got our sigma x1, it's in the probability one, I bet. Probability slide deck calculating this. So the same way that we did it before, how do we calculate sigma x squared given a bunch of numbers? How did you do that in high school? How do you calculate your variance given a list of numbers? There's an equation. How do you calculate? How do you calculate variance? Here we go. How do you calculate variance? You take your data minus your mean, multiply it by your data minus your mean, divide by n. But now you guys are smarter and you know instead you should really divide by n minus 1. Why? It's an unbiased, on average, more accurate. So here's an example of a 2x2 covariance matrix. So you're going to take your 10 A's. And you've got a vector for your X in your 10 A's, your first A. You've got your mean across your 10 A's. Again, this is an 8x1 vector. This is an 8x1 vector. Then if we're doing the top left, we're going to take the mu, sorry. So for the top left, for sigma x squared, we're just going to take, not that one. M00 minus the mean of M00 . We're going to add all those up, divided by n minus 1. So take whatever your M00 measurement is for your first A. Subtract the mean of the M00 measurements for all the A's. Take your measurement of the first A, M00 from the first A, minus the mean of the measurements of all the A's. Multiply those. Then take your M00 for your second A, minus the mean of all the M0s for the A. M00 for the second A, minus the mean of the M00 for the A's. We go through that for all 10 A's. Add them up, divide by 9. That's going to get you the first element. For the second element, we're going to take the first feature and the second feature. M00 mu 02, or is it 20? 02. So we're going to take an M00 . We're going to take for each of your A's, your M00 minus the mean of the M00s for the A's, and your mu 20 minus the mean of the mu 20s for your A's. For A1, for A2, for A3, down to A10. That'll get you that one. And coincidentally, because of the commutative property, we'll get you that one. The covariance matrix will be symmetric. Yes.
Part 2, instead of just doing all
All the numbers. Yep. All the letters. Or you can calculate the 10 individually and average them. It adds the same. Okay. So for the third, instead of mu 20, that's going to turn into mu 11. It's going to give you the third one. And you're going to do this for the A's and the C's and the E's all the way down to your Z's. A bunch of for loops in there. Unless you can do it with matrices, because it's an outer product of matrices. So you can get one instance across all 10, all 8 features by one outer product. If you do those as an outer product. If you want to check your numbers for your covariance matrix with me, just email me or bring your laptop here to class. I'm willing to tell you whether you did it right or not. Sort of, maybe. Finish up homework 3 first. Get that off your to-do list. And then I'll have the project posted this weekend. But I think the homework will keep you busy for a little bit, since very few of you have actually started looking at it. Okay, any other questions? Have a good weekend.